Hello, this is Naveen S. Sapare, Assistant Professor, Department of Mathematics, KLIT Hubli. So here I am with you to discuss about the topic Fourier transform. What is Fourier transform and what is the use of it? What are the applications? This Fourier transform decomposes any function as the sum of sinusoidal basis functions. And this basis functions is a complex exponential into the frequency. That is, this Fourier transform transforms a given function which is in a time domain in terms of the frequency domain. Okay, sometimes what happen, we get many difficult problems where it become very much necessary to transform the given function which is in a time domain, converting or reducing into the frequency domain form, which makes a problem solving simple. In such cases, we use this Fourier transform. And what are the uses, what are the applications of this Fourier transform? So the main use or applications of this Fourier transform is mainly in image construction, image analysis, image filtering, okay, and image processing. So in all these fields, we can use this Fourier transform. Example for this Fourier transform is, think that you are traveling in a road and some thieves took your pocket and ran by their vehicle. Suddenly, your friend beside you took a photo of that vehicle, and when you saw that vehicle, you came to know that the photo which is little bit blur. Obviously, when the photo is blur, then we cannot see the image properly, or we cannot read the number plate of that particular vehicle. In that case, how to find or how to see that number clearly? What is the technique? So in such case, we use this Fourier transform, which reduces that blur image in terms of a clear image, so that we can read the number plate of the vehicle. And if you know the number of the vehicle, then easily we can get the thieves which have taken your pocket. So this is a small example or application of this Fourier transform. Now, mathematically, how we are going to define it? Okay, mathematical form of Fourier transform. So how we can define it? Infinite Fourier transform. Infinite Fourier transform, or a complex transform. Okay, or complex, we can say, or complex transform of a given function f of x, of a given function f of x is denoted and defined by denoted and defined by f of x is equal to f of u, which is equal to integral between minus infinity to plus infinity f of x into e raised to plus I of x with respect to x. So this is the mathematical form of Fourier transform. So how to define it? The infinite Fourier transform or the complex transform of the function f of x is denoted and defined as f of x is equal to f of u, which is integrated between minus infinity to plus infinity multiplied by e raised to I of x, provided its limit exists. Its limit exists. And if the limit exists, then definitely it will be a function of u. Okay, so then we call that function of u as a Fourier transform of the given function f of x. Okay, so this is the mathematical form of a Fourier transform. So I just explained what this function do here. Obviously the function f of x will be in the time domain, and when you use this Fourier transformation, then definitely this formula will reduce the time domain function as a frequency domain functions, which will be used in many applications. Similarly, the Fourier transform inverse Fourier transform inverse Fourier transform of f of x is defined and denoted by f of x is equal to 1 upon 2 pi integrated between minus infinity to plus infinity. It is f of u e raised to minus I of x with respect to u. So this is the inverse Fourier transform of the given function f of x. Inverse Fourier transform of the given function f of x is defined and denoted by f of x is equal to 1 upon 2 pi integral between minus infinity to plus infinity f of u into e raised to minus I of x with respect to u. So what is the inverse Fourier transform do? Inverse Fourier transform of f of x reduces the function which is already in the frequency domain in terms of a time domain. Okay, so what this Fourier transform do? This Fourier transform transforms a time domain in terms of a frequency domain, but inverse Fourier transform will transform a frequency domain in terms of a time domain. So that is the difference between Fourier transform as well as inverse Fourier transform. So now we will solve some problems on the Fourier transform as well as frequency transform. Let us take a problem. Find the complex Fourier transform. Complex Fourier transform of the function f of x is equal to, it is defined as 1 for mod of x less than or equal to a, and it is 0 for mod of x greater than a, and hence evaluate integral 0 to infinity sin x by x with respect to x. Okay, so in this problem they are asking us to find the complex Fourier transform, and the function f of x is defined as 1 for all mod x less than or equal to a, and it is defined as 0 for mod x greater than a, and later we need to evaluate this integral. Okay, so how to find the complex Fourier transform or maybe infinite Fourier transform? So we have a mathematical form of a Fourier transform, that is f of u is equal to integral between minus infinity to plus infinity f of x into e raised to iux with respect to x. This is the Fourier transform of the given function f of x. But here f of x is defined as 1 for mod x less than or equal to a, and it is defined as 0 for mod x greater than a. And since we know that mod x is nothing but x lies between minus a to plus a. Okay, mod x is nothing but, obviously if I am taking mod x as less than or equal to a, it means that x is lying between minus a to plus a. Therefore, this mod x less than or equal to a implies that x is lying between minus a to plus a. So, for the range minus a to plus a, the function f of x is defined as 1, and for mod x greater than a, mod x greater than a means definitely here x is greater than a. X is greater than a means the range of x value is from a to infinity. So for a to infinity, the function f of x is 0. Therefore, we ignore this second part and we take only this first part. Mod x is less than or equal to a means x lies between minus a to plus a. Therefore, I will change the limits as minus a to plus a, and f of x is given as 1 here. So f of x is 1 and remaining is e raised to iu x with respect to x. Now we need to integrate this and we get here integration of e raised to iux is e raised to iux divided by iu, and applying the limits minus a to plus a here. Now applying upper limit first, then minus of lower limit. So we have e raised to aiu and lower limit minus of e raised to minus iau divided by iu. So this is nothing but f of u here. So we can simplify it further. Since we have a basic concept here, just we know that sine ax, okay, sine ax plus, it is I into sine ax plus cos ax is nothing but e raised to iax. Okay, cos ax plus I sin ax is nothing but e raised to iax. In a similar way, cos ax minus I sin ax is nothing but e raised to minus iax. So if you add these two equations, okay, when you add these two equations here, sine and sine get cancelled. Obviously when you add it, sine get cancelled, you will get 2 cos ax, you will get as 2 cos ax is equal to e raised to iax plus e raised to minus iax. In a similar way, if you subtract this as a first equation and this as the second equation, and if you take 1 minus 2, then definitely cos ax and cos ax get cancelled and this becomes plus I into sin ax plus I sin ax plus I sin ax become 2I into sin of ax, where we are subtracting 1 and 2. So we have here e raised to iax minus of e raised to minus iax. So it means from this expression it is clear that sin ax is equal to e raised to iax minus of e raised to minus iax divided by 2I. So therefore, I am replacing this e raised to aiu minus of e raised to minus iau, comparing with this equation becomes here f of u is equal to, it become 2i into sine of au. Okay, here we are having x, but here we are having u. So 2i sine au divided by iu here. So that is nothing but I get cancelled, and we have here 2 times of sine au divided by u. So this is the Fourier transform of the given function f of x. Okay, so this is the first part of this question. In a similar way, now we need to evaluate this integral. We need to evaluate this integral means we need to find out the value of the integral 0 to infinity sine x upon x. Obviously, this second part, that is evaluation of integral, is done by inverse Fourier transform formula. So for that we have here, now to evaluate the second part, now we have inverse Fourier transform, inverse Fourier transform. We have a formula here, f of x equal to 1 upon 2 pi 0 to, that is minus infinity to plus infinity, f of u to e raised to minus iux with respect to u. So this is the inverse Fourier transform formula. So by using this formula we can evaluate this integral. And one more thing, always you remember, when you are finding the complex Fourier transform and later if you are evaluating some integrals in the same problem, then definitely we can expect the answer from the first part which resembles to the integral which is given in the second part. Here you are having sine x upon x in the second part, therefore we can expect the answer from the first part which must resembles to this part. Maybe some constants will be there, but there should be the expression of the form sine x upon x in the answer of the first part. And since here we are having the answer of the first part which very much resembles to the integral we are evaluating in the second part. So now we are having f of u. So by using this f of u, we need to evaluate this integral. That's why we are using the inverse Fourier transform formula, and we substitute this f of u and we try to evaluate this integral. So here it is 1 upon 2 pi. So it is minus infinity to plus infinity. F of u is nothing but it is 2 times of sine au divided by u into e raised to minus iux with respect to u. One thing you can remember here, that in the second part actually we are not going to integrate anywhere. We just try to reduce it, try to simplify it so that we can bring this integral into this form. So in any of the step we are not going to integrate it. We just try to reduce by taking some substitutions, just by replacing some variables and so on. Okay, so now obviously here 2 get cancelled, and since we know that, just observe this second part. In this second part we are having only sine x upon x. We don't have any a term here or a constant like, but here we are having sine au. Here we are having a. Just observe, when you replace u as x, then definitely we can get a expression like sine x upon x, but extra function or extra constant is a here. So we can replace this a as 1, or we can substitute a value as 1 so that we can reduce this integral into the required integral. And also in the required integral we do not have exponential function, that is e raised to iux. It means that we need to reduce this e raised to iux as 1, so that we can bring this expression sin x upon x. So here I will take a substitution, that is a equal to 1 and I put x equal to 0. Okay, why I am taking this a as 1 and x equal to 0? It is because from this expression I need to bring the expression sin x upon x, so that I can get the value of the integral sin x upon x. That's why I am putting a equal to 1 and x equal to 0. It's just a guesswork just by observing the given integral. So putting a equal to 1 and x equal to 0, this f of x becomes f of x equal to, it is obviously 2 and 2 get cancelled here. So remaining is 1 upon pi integral minus infinity to plus infinity, and when I am putting a equal to 1 x equal to 0, it becomes sin x by x with respect to, it is u, sorry, it is sin u by u. Okay, sin u by u. So almost we are at the answer. Now replace, now replace u as x. Okay, now replace u as x. So we have f of x is equal to 1 upon, obviously here we have taken x equal to 0, so this f of x become 0 here, and here also it become 0. Therefore 1 upon pi, and this is minus infinity to plus infinity, sin x by x with respect to x. Almost we are done, and now we need to have the value of f of 0, because we have taken here x equal to 0, so this f of x become f of 0. So this is f of 0, here also f of 0. Then what is the value of f of 0? F of 0 means the value of the function f of x at x equal to 0. So where that x equal to 0 lies? Obviously x equal to 0 lies in this range. So at x equal to 0, the function is defined as 1. So we replace this f of 0 as 1 here, and here it is 1 upon pi, and then minus infinity to plus infinity, sin x by x with respect to x here. And still it is not completed, because we must have the limit between 0 to infinity. And since we know that sin x upon x is a even function, that is, we know that if f of minus x is equal to plus f of x, then we can say that such function is a even function. And we have the property in integral that 2 times of, that is, integral minus a to plus a f of x dx can also be written as 2 times of 0 to a f of x dx. Okay, this is the properties of integral. Integral between minus a to plus a f of x dx can be written as 2 times of 0 to a f of x dx if the given function f of x is even. That is, f of minus x is equal to f of x, then such function we call it as a even function. That time we can write the integral minus a to plus a integral f of x dx as 2 times of 0 to a. Therefore here also minus infinity to plus infinity can be written as 2 divided by pi. Obviously here it becomes 0 to infinity, then it is sin x by x with respect to x. So now obviously the value of this integral, just taking this 2 upon pi this side, and the final answer we get as, here I will write, so it become pi by 2 is equal to integral 0 to infinity, that is sin x by x with respect to x. Hence this is the evaluation of the integral.